Today's lesson is going to be on section 9.6, which is about counting principles. There's two big vocab words. The first one's kind of an important one. It's called replacement. It's when you observe a value and then you replace it so it may be observed a second or third time, many times. This one is a big one. You'll know that it's going to be coming into play because they'll usually talk about it in the example problems. The other one, order, is an even bigger one and the most important one of today's lesson. Order is when chronology has an effect on the outcome. That means you might be interested in having something occur first, or maybe you might be more interested in having it occur last. If that comes into play, that means order is important. That's not going to be something that's going to be just given to you. You're going to have to decide if order is important given the context of the situation. Let's take a look at a couple of example problems. So to begin with, our first example problem says, determine how many ways a computer could randomly generate two integers from 1 to 12 whose sum is 6. So what I like to do sometimes is I like to make a list, and so I've actually started on the list for you right here. 1 and 5, those add up to 6, so that would be a good combination. Similarly, 2 and then 4, if you got those two numbers, they would add up to 6. 3 and another 3, those ones is a repeat, but that's okay. It didn't say that we couldn't do it, so we get to repeat if we want to. Then after that, then what you do is you would have 4 and then 2. This is technically different from this one because the 4 is first and the 2 is second, as opposed to over here where the 2 was first and the 4 was second. And then lastly 5 and then 1. You can't do 6 and 0 because 0 is too small, and you can't use any of the other numbers because they're too big. So we have these many outcomes. There's a grand total of 1, 2, 3, 4, 5 possible outcomes. 5 different ways to come up with those different constraints. That's a really, really nice, easy way to do it. And there's times in the homework where they ask you to come up with a list, so you can do it the exact same way that I did. Next example is very, very similar, except there's a slight change on it. It says determine how many ways a computer can randomly generate two distinct integers from 1 through 12 whose sum is 6. That's going to be almost the exact same thing. The word distinct in here makes the difference though. Distinct means you can't have the same number showing up twice in a row. So that means 1 and 5 is okay, 2 and 4 are okay, and similarly 4 and 2 and 5 and 1 are okay. The one that is not okay is 3 and 3 because it's the same number twice in a row. Because of that word distinct right there, that means you can't use the 3 and 3. So for this time, there are only 4 outcomes that are available to us. Now those are great. Those are also really simple because you can make the lists. What about if things get a little bit more intense? If things get a little bit more intense, then we got some principles and some rules that are going to help us out. We also have some tricks that we're going to use our calculator for. One of the first ones is the fundamental counting principle, which I have for you right here in this box. If you have two events that occur, and the first event occurs m ways, and the second event occurs n ways, then you can figure out how many ways they both occur at the same time by doing m times n. Just do a little multiplication so you don't have to write out the list. Similarly, if you have more events, so if your first event occurs m ways, your second one is n, and then your third one is p, all you need to do is just more multiplication. That is going to be m times n times p. First one and the second one and the third one. If you can use the word and, that usually means you need to multiply. So that's what we got going on right here. Let's use that counting principle right here for this license plate problem. Now I'm going to warn you, I wrote this license plate problem very ambiguously because I want to talk about the different possibilities, so we'll do that in a couple of seconds. So our example problem says a new license plate consists of 2 letters followed by a 4-digit number. How many distinct plates can be formed? Well, there's a couple pieces of information in here that you need to be privy to, or the book is assuming that you know, and that might not necessarily be true. So the first thing is you need to know how many letters are in the English alphabet. So in the English alphabet, there are exactly 26 letters. I get a lot of people who tell me that there's 24 letters or maybe 25 letters, but 26 letters is the actual amount. The second one is the one that really trips people up, is they think about the word digits. Now digits are just the simple numbers, and so what a lot of people think is they think, oh, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 digits. Well, that's not quite true. There's also one other digit that's actually a little bit smaller, which is 0. So in total, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. There are 10 digits available to you. So those are the two pieces of information. Now let's set up our problem. It says that we want 2 letters and we want 4 digits. Something that I like to do, and you don't have to if you don't want to, but it's a great way to show work, is I actually set up blanks. I'll make a blank for each time I need to write a letter. And I know that these things are going to get multiplied. Then I'll also create a blank for every time I need to write a digit. So I have going to have 2 letter blanks, and I'm going to have 4 digit blanks. Each of these facts is going to get multiplied by the other facts because of the counting principle. Now, we know that we have 26 letters. So what we're going to do is we can have 26 letters here. And then it didn't really say that we couldn't replace it, so we're going to put another 26 letters here. As far as numbers go, we have 10 digits available to us, and then another 10, and then another 10, and then another 10. So we're going to have that guy right there. So now this is a really great way. You can type that into your calculator and multiply all the way across. Another way that's a little bit more simple would just be if we did 26 squared, because there's 2 of those, and 10 to the 4th, because there's 4 of those. And that makes it a little bit easier to type into your calculator so you don't have to work as hard. If you do it that way, you're going to get a big fat number, and we're just going to write it out with decimal or digit by digit. That's going to be 6760000, and that would be license plates. This is a story problem, so we need to put a unit on there, so that would be plates. Now you might say, hey, Mr. Slomka, I don't know if I totally buy that. There is the word distinct in there. And so because of that word distinct, shouldn't you be changing the numbers because you can't use the number a second time? And shouldn't you be changing the letters because you can't use the letter a second time? Well, yeah, that's something to talk about. So you have to look at where the word distinct is used. Distinct is used on plates. It doesn't say that you have to use distinct numbers or distinct letters. So each plate just has to be different. And this covers those distinct plates. If the word distinct was on the digits and on the letters, the problem would look slightly different. If it was on those things, then it would actually be 26 times 25, because once you used this letter right here, you couldn't use it again, so you'd have less options available to you. And for the numbers, it would be 10 times 9 times 8 times 7. Hopefully those seem a little bit familiar to you. Those are kind of like factorials. They're shut off a little bit too early, but that is the same kind of thing. I could definitely do that to a problem like this. I could move the word distinct onto the letters and the numbers, and then you would have to change the calculation. This is an important differentiation right here, and you need to make sure that you're reading the problems closely so you know which one is the one that you're going to be after. If you are calculating this bottom one, your value that you're going to get is slightly different. That one's going to be 327, then 6000. So something to look at here is which value is the bigger one and which value is the smaller one. That's an interesting thing to look at as well. This bottom one leads me into another topic, which is interesting, and that topic is called a permutation. Yesterday I had mentioned that we were going to talk about permutations, and here they are. They show up in 2 different flavors. The ones that we are looking at right now are all pretty simple, and so they're called simple permutations. And if you look closely, you'll notice that it's just a factorial, which is something that we've done before. You can either count up to the value n, or what I like to do is I like to go backwards and I count down. The other version is a little bit more intense, and this is the one that we'll see a lot more often. And this one is very similar to the combination that we were talking about yesterday. Instead of NCR, this one is NPR. And it's going to be the n factorial over n minus r factorial. If it was a combination, there would be an extra r factorial at the back on the denominator here, but it's not. It's only a permutation, so it's just n minus r factorial. That's it. Let's try calculating with this second one right here, and we'll just practice a couple of these ones. Kind of like yesterday, when we do these ones right here, you'll notice that a couple of them have asterisks, and that's because they're extra special ones, and those are the ones you don't need to show work for after we do these first couple problems. So let's take a look at a very basic one, 5p3. This one doesn't have a word for the p. Sometimes I slip and I say choose, but it really doesn't have a word. So we're just going to use the 5 with the p for permutation and the 3. The 5 is the thing that's going to go on top, 5 factorial, and both the 5 and the 3 are going to be used in the denominator. They're going to be subtracted. So it's 5 factorial over 5 minus 3 factorial. If we simplify that a little tiny bit, that's going to be 5 factorial on top over 5 minus 3 is going to be 2 factorial. If you write it out the long way, that would be 5 times 4 times 3 times 2 times 1 in the numerator, and in the denominator it would just be 2 times 1. Like we've seen many times before, this leads to a situation where things can cancel out, and you're basically left with just 5 times 4 times 3. That's not that difficult to calculate. I could put a question like this on a no calculator portion, and the value for this would be 60. Now, even if I put it on a no calculator portion, I'm still not going to have you memorize the formula. So that one, I'll give it to you. That one's not a problem right there. So if you need it, I'll provide it for you. Next one's a special one. It's got the asterisk back there. It's similar to yesterday. It's special because it ends with a 1. Let's see what we get when we have a 4p1. Well, it's going to be 4 factorial on top, and it's going to be 4 minus 1 factorial on bottom. Well, that bottom factorial, 4 minus 1, is going to just be 3 factorial. And these guys are going to share a lot in common. 4 times 3 times 2 times 1 is the numerator, and just 3 times 2 times 1 is the denominator. Cancel, 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 and you end up with a value of 4. 4p1 is 4, 5p1 is 5, 18p1 is 18. So that's a nice pattern that you can use. You don't have to show the work anymore. Let's try a big ugly one right here. 8p5. So now this one is so big and ugly that you probably wouldn't be able to do it without a calculator because there's a lot going on here. So 8 factorial, that's going to go on top. Then we're going to have our 8 minus 5 factorial on bottom. 8 minus 5 is going to give you a factorial of only 3 in the denominator. So that makes me nervous because I know that I'm not going to have that much in the denominator, and that means not a lot is going to cancel out. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 in the numerator, and only 3, 2, 1 in the denominator. That's not that much, so not that much cancels out. Now it's easier. 8 times 7 times 6 times 5 times 4, that's pretty nice, but it's still too big for a no calculator portion. The value that you actually end up calculating is 6,720, so that's much too big for a no calculator portion right there. Next one's another fancy one, 18p0. For that guy, that is going to be 18 factorial on top and then 18 minus 0 factorial on bottom. Doing that subtraction is just going to give you 18 factorial over 18 factorial. Same on top, same on bottom. The answer for that one is 1. 18p0 is 1, 20p0 is 1, 5p0 is 1, so you'll get 1 every single time. Last one is the double trouble. When we saw a double trouble last time, it also had a value of 1. Let's see if we get 1 for our 9p9. So for that guy right there, that would be 9 factorial over 9 minus 9 factorial. Now, if you remember, 9 minus 9 is actually going to be 0, and you can take 0 factorial. 0 factorial is just 1, so that's going to be 9 factorial over just 1. And that means that 9p9 is actually equal to 9 factorial. That's the special fact about it. But 9 factorial is still a really big number, so when you look at the actual number, it doesn't seem that special. It's going to be 362,880. So that big number is not so special. The fact that 9p9 is equal to 9 factorial, that's the special part. On the next side, what we've got is we've got a couple of story problems, and these ones are a little bit more par for the course, but they're still pretty basic. So what we have is we have Mr. Tracy taking his wife and his 4 children to go get his family portrait taken. And what we have going on here is we want to know how many ways the family can line up to take the picture. So what a lot of times happens is what they'll do is occasionally they put the tall people on the outside edge, and then they put the short people in the middle. That's a popular one to do, right? Anybody stand for that picture? Or, I don't know why you'd ever want to do this, but you could line up from tallest to shortest, which seems like a really weird picture, but something you could do. So, that's another possibility. We have to figure out all the different possibilities that you could create. So now, for a situation like this, if you want to, you can set it up kind of similar to what I had on the front side. You can set it up with blanks. So what we have is we have Mr. Tracy, his wife, and 4 kids. So that means there are going to be a total of 6 people in this picture, and so I'm going to have 6 blanks. Now, I'm not saying you need the blanks. You can figure it out probably on your own, but the blanks help me, and they might help you as well. So for the first spot right here, you can put anybody in there because nobody's posing yet, so that would be 6 people available to you. Now, as soon as that person's standing there, you're 1 person short, so now you only have 5 for the next one. And then similarly, 4 for this one, 3, 2, and by the time you get to your last spot, there's only one person that's not in the photo yet, so you only have one option available to you. A faster way to write this would just be 6 factorial. And to get the calculated value, you can just use your normal factorial button, which is no big deal. There are 720 ways to stand for this picture. Once again, this is another story problem, so you need to put a unit on there, so we're going to make sure we put a unit on. Ways is always a pretty safe bet, or outcomes is a pretty safe bet. You really can't go wrong, but I am going to be looking for those units. Now this next one adds a little bit of a twist, but it's still not too much. How many ways can the family sit in their miniature van on the way home if Mr. Tracy insists on driving? So what we have is we have Mr. Tracy taking the driver's position. He's the only one who's going to be able to drive, and then everybody else is stuck in the back. So we still have to fill the minivan with the 6 people. Here's the driver's seat right here. Now, if Mr. Tracy insists on driving, that means that there's only one person that's going to be able to drive. Then there's 5 people to sit in the back of the van. 5 could go here in the co-captain's chair, and then we've got 4, and then 3, and then 2, and then 1. So even though there's 6 people, what we're really going to do is we're just going to be calculating 5 factorial to get your value right there. So Mr. Tracy is limiting the number of options that are available, and that might just be because he doesn't want any of his young kids to drive. So now if you only have 5 factorial, the amount is much smaller. It's only 120 ways that they can drive home, which is a bit smaller. Same amount of people, almost the same situation, but a much smaller answer. Now listen closely to these next 2 problems. These next 2 problems are really, really big on order, as I had mentioned on the front side. I want you to listen to them and think about them, and I want you to think about which one has order that is important and which one has order that really doesn't matter. So we have this really great company, Google. Google has just posted job openings in its product testing and development department, its corporate sales department, and its code monkey department. 87 people have submitted applications for these jobs. How many ways can the company fill the positions with the given applicants? Now let's take a look at the second one. The second one says Google has, once again, 3 openings, but they're all in the same department. They're all in the janitorial department. Now, I think I'd be really excited to work for Google, but I don't know if I want to be washing toilets for Google. 87 people have once again submitted applications for the job. How many ways can the company fill the positions given? One of these has order that is important, and the other one does not. So specifically, the first one, order, is very, very important here. There are jobs here that I would love to have. I would love to be in product testing and development. I want to wear a Google Glass. It looks sweet. I wouldn't mind making some corporate sales. That seems okay. I bet you get paid a lot. And the last one, corporate monkeys. One of the reasons why I became a teacher is because I didn't want to stare at a computer screen all the time. So I don't think I want to be a code monkey. So order is extremely important. Because order is important, that means we're going to be using a permutation. So now here's the cool thing about permutations. What we're going to do is this one's going to be our first advanced permutation. You're going to write down your big capital letter P, because order is important. And then what you're going to do is in front of the capital letter P, this is the number of things that are available to you. Not necessarily all the things that you need to take, but they are available to you. Behind the capital letter P, this is going to be where you put the things that you actually choose. I know it's a little bit of a cheat to use that word because it's not a big capital C, but we'll use it anyways. So available. We have 87 people that are available to us, and we will be only choosing 3 of them because there's only 3 positions in the testing, in corporate sales, and code monkey. So it'll be 87 P3. So when you calculate that value, you can do it on your calculator. What you need to do is you just need to find the NPR option on your calculator. It is right next to the NCR option that we used yesterday. See if you can find that NPR option on your calculator. If it's a TI-84 or higher, it is going to be under the math menu and the PRB menu, which stands for probability. When I type this into my calculator, then I am going to get a value which is very large, and there are 635,970 ways that I could hire people for this position. Now for the second one, this one, you're getting hired as a janitor. No matter if you get hired first or if you get hired last, you're going to be a janitor. So order is not as important. So for this one would use a combination, which we will talk about in a couple of seconds. We'll get back to this guy in a little bit. But before we finish up right now, let's say order is not important. So for our next piece, what we have is we've got something that shows up quite a bit, and it's taking words that already exist and reorganizing them to create something that the book calls quote-unquote code words. It says how many distinguishable ways can the letters in each word be written. So the first word is car. It's a nice short word, and it's got some good properties here. So if you have these three letters, you could write them as C-A-R, and that would be a word. Or you could write it as C-R-A. That would be another word. Cra. I don't know what that word means, but it's a word. Similarly, we could start with the R, and we could do R-C-A, which is Rika, or R-A-C, which is rack. That's not as bad. If you started with the A, you could have A-C-R, which is Acker, or A-R-C, which is one of the only other words that actually is real, arc. That gives you a grand total of 1, 2, 3, 4, 5, 6. There are 6 different ways to create some new words from the word car. If you wanted to do that in a different way, you could easily do that. That is just a simple permutation. You have 3 letters available for your first slot, 2 letters available for your second, and only 1 letter available for your third. So that is going to be 3 times 2 times 1, which is 6, or 3 factorial, which is also 6. It's a nice simple permutation. Order is important. When you change the order, the word changes. Now, when the words get a little bit more complex, it becomes a little stranger. What I was doing here is a lot of times I was just switching the last 2 letters. In this word, Mississippi, if you start switching some of the letters, it really doesn't make another new word. Like these S's. If I change the location of these 2 S's, if I just switch them, it's the same word. Or these P's right here, if I change the location of those 2 P's, it's still Mississippi. So there's a rule that will help you out for that, and it's going to be this guy right here. What you do is you use the number of letters on top, and then if you have any repeats, you're going to put them down in the denominator with their own factorials, and you write the number of times the letter appears. So let's do it for this Mississippi word. How many letters are in the word Mississippi? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 letters in the word Mississippi. A lot of them are used more than once, but there are 11 in total. Then let's talk about some of those letters. S. S is a very prominent letter in the word Mississippi, and it shows up 4 times. So for S, we're going to have a 4 factorial down there. That covers all of these S's. I is another very prominent letter in the word Mississippi, and it also shows up 4 times. So it's going to get its own 4 factorial. And the last letter that shows up a couple times is P. P shows up twice. So for P, that one's going to get a 2 factorial. Now you might say, hey, Mr. Slomka, what about the M? Well, M only shows up 1 time, so that'd be 1 factorial, which is pretty useless. If you multiply all these terms that are in the denominator and then do your little division, you will get the number of possible words that you can remake that actually sound different, which would be 34650, 34,650. That's a lot of words. I definitely wouldn't want to write a list like I did for over here for car for the word Mississippi. Let's take a look right down here at our definition for the term combination. Combination is the number of outcomes from n objects chosen r at a time. What we have is the same thing that we were using last time. Here's another new way to write it as well. It's actually a permutation that's being divided by r factorial. Let's use this idea right here and this fact right here to answer our Google question that we were talking about earlier. Permutations are when order is important. Combinations are for when order is not important. So up here for our Google problem, what we had is we had 3 positions. They were all in the janitor closet, so that wasn't very nice. So what's going to happen is because the order is not important, if you get hired first or last, you will be a janitor. We're going to use a combination. That would be 87 people applying, and we would be choosing 3 of them this time. And because it's a combination, it's not as exciting, and we are going to get the value 105995 ways. Now, once again, similar to what we had done before, it is interesting to usually look at the 2 things and see which one's bigger and which one is smaller. That is important information that will help you rationalize and understand your answer a little bit more carefully. So those are 2 good ones. On the back here, what we have is we've got some card problems. Now, card problems can be pretty easy if you are familiar with a deck of cards. If you're not familiar with a deck of cards, I would highly recommend that you get a hold of a deck of cards and you start familiarizing yourself. So, with a deck of cards, there's a couple facts. You have a couple of suits. You have 2 dark suits and you have 2 red suits as well. So, some of the suits that we have are we have the diamonds and we have the hearts. We also have the spades. I'm a bad spade drawer, I'm sorry. Not too bad. And we also have the clubs. I'm not particularly great at that one either. The diamonds and the hearts are the red ones, and they make up half of the deck. The spades and the clubs are the black ones, and they make up the other half of the deck. Okay, let's try some of these playing card problems. So for our first one right here, it says that we want 5 red cards in our hand. Now, what you're going to do is you're going to use a combination for this one because order is not important. If cards are dealt to you in a certain way, that doesn't mean you need to play them in that exact same way. You get to choose the order that you get to play them in. And in fact, you even get to choose the order of the way that you want to hold them in your hand. It doesn't matter. It is your choice, so order is not important. What we're going to do is we're going to set up a big capital letter C, and then in front right here, what we need to do is we need to set up the number of cards that we're going to be choosing from. Now, a lot of people are going to say, oh, there's 52 cards in the deck, so I'm going to choose 52. That's not quite the case. We are only interested in the red cards, so we only want the red cards. Half the deck is red, so you're going to do 52 divided by 2, which is going to be 26. Then, of those 26 cards, we'll be choosing only 5 of them. Calculate that with your combination on your calculator, and you get this value right here. Let's do one that's a little bit tougher. For our next one we have right here is we've got 4 spades and 1 card that is not a spade. So for 4 spades, spades is one of the 4 suits that we have available to us. It's the one that kind of looks like a shovel. And we only want to draw from those cards right there. Now because it's one of 4 suits, you're going to do 52 divided by 4 to get 13 cards right there. We'll only be choosing 4 of them. Second part's a little weird. It says 1 card that is not a spade. Because it's not a spade, you need to think about all of the diamonds, all of the hearts, and all of the clubs. Now, you can rationalize this a couple different ways. Some people say, okay, there's 13 diamonds, 13 hearts, and 13 clubs. Add those 3 up, and you get 39. The other way that people will think, okay, there's 52 cards. I'm going to subtract out the spades that I don't want. 52 minus 13 also gives you 39. Now, we only want 1 of these, so it's going to be 39. Choose 1. You multiply these 2 pieces together, mostly because of the word and right here, and you get this value right here for your number of hands. Once again, still story problems, so you got to write a unit on there. 2 more. 3 face cards. Now, when I say face cards, a lot of times people ask me about ace. Ace does not have a face. There are no eyes, no nose, and no mouth. So the only face cards are the ones that have faces. Kings, queens, and jacks. So we have 3 face cards and 2 cards that are, once again, not face cards. This word not is really going to come up a lot in our probability discussion, and it's going to be powerful. So it's good to get used to it now. So let's talk about face cards. There are 3 of them, and there's 3 diamond ones, 3 heart ones, 3 spade ones, and 3 club ones. That means there are a total of 3 times 4 or 12 face cards available to us. We are only interested in having 3 of them, so it's going to be 12, choose 3. Now for the other part, what's going to happen here is we want 2 cards that are not face cards. So what you could do is you could try to think about all the cards that are not face cards, like 2s and 3s and 4s and 5s and 6s and 7s, or what you could do is you could just take the number of cards you have in total and subtract the face cards from it, which is the way that I like to do. So I would do 52 cards minus the 12 face cards. That's a little bit easier for me to understand. That means there are 40 cards that are not face cards. I only want 2 of them, so I'll do 40, choose 2. Calculate both of these combinations, multiply them together, and you will end up with 171600. There's so many possible different hands available to you, and that's why some people say that cards is a game of chance. Other people would argue that there's only a finite certain number of hands, so it's a game of skill. Last one right down here is another weird word term that's going to show up a lot. At most 1 diamond. At most right there and its brother at least are real pains in the butt, and they will cause you issues. So you need to watch out for them, because if you don't, then and you just bulldoze your way through the problem, you'll miss half the work. At most one diamond means it could be one diamond or less than one diamond. So specifically, if you wanted to be very specific, that would be one diamond or no diamonds. That would be okay as well. So let's talk about that. So for our one diamond case, what's going to happen here is we're going to have 13 diamonds available to us, and we'll be choosing one. Now, that's only one of our cards. We have 5 cards that are supposed to be in our hand, which means we're going to have a couple more cards that are not a diamond. There are 39 other cards in the deck that are not diamonds, and we're going to have to choose 4 of those. So we're going to have our combination right there. That's our one diamond case. Then for the 0 diamond case, this one's a little bit easier. It means we want no diamonds. All the cards are going to be not a diamond. So of the 39 cards that are not a diamond, you will be choosing all 5 of your cards. So now this time I have multiplication happening here and I have addition. And the reason I have addition is because of the word or. One diamond or no diamonds at all. So that would be a plus problem. So we have multiplication here because it's and, one diamond, and 4 not a diamonds, and over here is or, so we have plus. If we add those 2 pieces together, after we calculate everything out, we should end up with 1645020. That is your number of hands. There are 2 more problems down here about Mr. Book and auditioning for the play, and I want you to see if you can go through those problems on your own. The main thing that I need you to focus on is whether they are permutations or combinations, if order is important or if order is not important. We can talk about the answers of those 2 tomorrow when I return. I hope this video lesson worked out, and if there's any issues, we will also discuss those tomorrow as well. Have a good day. Bye-bye.